Hello everyone and welcome back to the channel. We all understand what a database transaction is. A set of operations that must either all success or all fail, ensuring atomicity. But what happens when that transaction needs to be spanned across multiple independent databases or different microservices? This is the complex world of distributed transactions. In system design interviews, demonstrating how to tackle this challenge is crucial for building reliable, consistent systems. Today, we are diving into what distributed transactions are, the problem they solve, and the common approaches to implement them. Okay, so let's first understand the problem. The core problem distributed transactions solve is achieving asset properties, atomicity, consistency, isolation, durability across multiple disparate data sources or services. Let's take an example to understand. So let's imagine an e-commerce order fulfillment process. We have e-commerce and we have like an order fulfillment process. When a customer places an order, your system must need to do some things. First, debit the customer's account in payment service database. Number two, we need to update the inventory in the inventory service database. Number three, we need to create an order record in the order service database. If any of these steps fails, all of them must be rolled back to maintain consistency. You can't debit the customer without updating the inventory and vice versa. Okay? In monolithic application, this might be single database transaction, but in a distributed or microservices architecture, data is partitioned across independent services, making this all or nothing guarantee incredibly challenging. Okay, so what is a distributed transaction? A distributed transaction is a transaction that spans multiple independent resources where all participating resources must either collectively commit success or collectively roll back, which is fail, as a single atomic unit. The ultimate goal is to maintain the integrity and consistency of data across these separate systems. Even when network failures or individual services crashes occur, it's about coordinating a global decision among multiple participants. Okay. So implementing distributed transaction is quite difficult, okay? But there are common patterns used to address that. We have the first one, which is the two commit phase, or 2PC. 2PC is a classic atomic commitment protocol. It involves a coordinating entity, often called a transaction coordinator or a global transaction manager, and multiple participants, which is the databases or services involved in this operation. There are two phases. The first phase, the coordinator sends a prepare request to all participants, but each participants perform all necessary operations, looks its resources and logs the changes, but does not commit these changes. Okay, this is pretty important. It does not commit the changes. If a participant is ready to commit, it responds yes. If it's not, it will respond no. After that, we will go to the second commit. If the coordinator receives yes from all participants, it sends a commit request to all. Each participant then commits its changes. If any participant responds no, or if the coordinator time outs, the coordinator sends a rollback request to all participants and they undo their changes. So they make changes, they don't commit it, they send yes to the coordinator. When the coordinator receives yes from all, it's committed. If it's not, it will send a rollback request. Okay, the pros of this type of commitment of pattern, it guarantees atomicity, basically all or nothing, across distributed resources. It's well understood and formally proven. But what are the problems? What are the cons? We have three things. First, blocking. Number two, single point of failure. Number three, we have a performance problem. Let's talk about the blocking first. But in terms of the blocking, participants hold clocks and resources from the entire duration of the transaction. If the coordinator fails during phase 2, participant might be left in unknown prepared state, holding locks indefinitely, leading to resource contention and reduced availability. This is often called the block problem or the blocking problem. Number two, we have a single point of failure. The coordinator is a critical single point of failure. If it fails at a wrong moment, it can lead to inconsistent status requiring manual intervention. Number three, we have a performance problem. It involves a significant network overhead, like multiple rounds of communication and higher latency due to blocking. So when to use this type of patterns? I would say generally for strong immediate asset guarantees across a few tightly controlled resources within a single organization's control, where blocking or temporary unavailability is quite acceptable. Okay, next we have Saga Pattern. The Saga Pattern is a way to manage distributed transactions in microservices by sequence of local atomic transactions. Each local transaction is committed by different services, by different service and publishes an event. This event then triggers the next step in the saga. If a step fails, compensating transactions are executed to undo the effects of previous successful steps. Okay, so it looks like that, as you can see here. So the pros of this one, we have non-blocking because services don't hold the distributed locks, improving scalability and availability. Number two, highly scalable because well suited for microservice architecture. Also, it loose coupling because services communicate via events, promoting independency. What are the cons here? We have some sort of eventual consistency. This is the biggest trade-off. Number two, you have increased in terms of complexity. So because it's significantly harder to implement events, writing all compensating transactions, and harder to debug due to its asynchronous nature, okay? Also, we have no atomic rollback. It requires explicit custom compensation logic. Also, we have atomicity is not guaranteed as strongly as 2PC, okay? But when to use this in microservice architecture where loose coupling and high scalability are paramount, and eventual consistency is an acceptable trade-off. Okay, so when to use which in your interviews? I would say in system design interview, when discussing atomicity across multiple data stores, or services, you can talk about 2PC or 2-commit phase. You can mention it for scenarios demanding very strong immediate asset guarantees, acknowledging its blocking nature and single point of failure. You can use a Saga pattern. You propose it for microservices, emphasizing its non-blocking nature, scalability, and loose coupling, while critically highlighting the shift to eventual consistency and the need for compensating transactions. You need to avoid the true 2PC across microservices. Generally, in modern microservice design, applying true 2PC across independent services is advised against due to its blocking nature and impact on availability. Okay, so how to discuss this in your system design review? You need to clearly distinguish between 2PC and Saga. Always discuss the trade-offs like blocking versus eventual consistency, simplicity versus complexity. Justify your choice based on the business requirements for data consistency, latency, and availability. It demonstrates a sophisticated and programmatic approach to handling complexity in distributed systems. So that's it for this video, and see you in the future.